Welcome to properties of the definite integral. So here we're working with a theorem, which is let f and g be defined on a closed interval I that contains the values a, b, and c, and let k be a constant. So again, we're looking on a closed interval I. So this is I. F is graphed somewhere above that, and A, B, and C are somewhere within. And then, of course, we have our function f graphed wherever. So this is f, however it looks. Then we have a few properties about the definite integral. So first up, we take the definite integral from a to a of f of x dx. Right? That means then that we're really just looking at on our graph, whatever f looks like, we're looking from a to a. Our little region has no width, right? So there's no width. And if we have no width, then we should have no area or zero area. So the rule is that if we take the definite integral from a to a, we don't change x values there. We have zero area and we just get zero. Next up, we were taking advantage of in the previous problem. If we want to find the definite integral, if we do the definite integral from a to b of f of x dx and add to that the definite integral from b to c of f of x dx, this should be exactly the same as taking the whole integral from a to c of f of x dx. So essentially what we're saying here is if we have our curve, we have our A, B, and C, we can find the area in pieces. So here's one piece. The second piece from B to C. Basically what they're saying is that if we take the area of the yellow and add the area of the pink, it's equivalent to taking the whole area, which that's exactly what we did before. So basically we have the overall area, whoops, is equal to what we shaded in yellow plus what we shaded in pink. So we're just breaking our area into chunks. Again, this is exactly what we were doing in the previous video, using our geometric shapes to find the total area. Next up is a slightly weird one, which is the integral from a to b of f of x dx is the same thing as negative times the integral from b to a of f of x dx. Or you could do that backwards and say the integral from b to a of f of x dx is equal to negative the integral from a to b. So essentially what we're doing for this is we're reading width backwards. So as we work our way from right to left, we're going to have negative width instead of positive width. So again, working right to left, width is negative. And so when we find area, we're going to be multiplying by a negative width instead of a positive width. All right, next up, we'll look more familiar. And these are similar to our two integration rules that we just were talking about in section 5.1. So the integral from a to b of f of x plus or minus g of x dx. We can split this into two integrals. We can go from a to b of f of x dx. And then a second integral from a to b, oh, this should be plus or minus. A second integral from a to b of g of x dx. I technically should say that for this, g is also defined on I. Right. So we saw in section 5.1 that we could split integrals across addition and subtraction. And here we're seeing that we can split definite integrals across addition and subtraction. Basically, if you think of it in terms of area, if we had like f plus g, you can kind of view it as here's f, and then if we add on g, so this is sort of f, and then if we add on g, whatever g does, so this is adding on g, then we're kind of figuring out, okay, we could take the area under f, and then we could add to that what would be the area under g. It's a slightly strange shape here because it's how it adds on top of f, but that's basically what we're doing. It's just adding the two areas. It winds up being the same. So this top function, what we're graphing here, is f plus g. And then we could start with f and add whatever function value g has at the designated x value to figure out the graph. And then last up, if we take the definite integral from a to b of k times f of x dx, that k can be pulled out front, and this is k times the definite integral from a to b of f of x dx. So you can kind of think of here, in this first case, k is multiplying the height. But when we're doing all of our area calculations, right, that height just multiplied straight into the area. And so that's equivalent to here, k is multiplying area. And the k just comes along for the ride. So if we multiply the height by some amount, the area will also be multiplied by that. All right, so those are the various properties of the definite integral.